All right. Okay, I'll just have to do it this way, and you'll have to listen if you're on the computer, but that's good. I'm John Land. I'm with the president of the club this year. And we have a couple of guests, new members. We got Stalings. Tell me your names. What's your first name? Don and Susan Saling. And the Walkers, tell us your names again. Deanna and Cameron. So they're here, and we got our senior member way back there, Mr. Ritchie. Everybody say hi to Ritchie. Good to have him here. And Miss Judy's here with us. So and there's Tamara. So we've got a good group here. And who we got coming in here? Oh yeah, that's Don. So that's good. Well, anyway, we're going to try to get through this tonight, and hopefully everything will work. But this is be our last meeting here at the Jinks Planetarium until this fall, but we'll still be having our regular observing nights and activities at the observatory. So welcome to you tonight. Let's go to the next slide there. Here's some kind of a program rundown. We've got our upcoming events, which I'll show you, and our summer astronomy conventions. And then we're going to talk about the total eclipse of the moon coming up this Sunday night. Looks like it's going to be clear. Brad's going to tell us a little bit about serving chairman plans, some volunteer opportunities, and if it will work, we have a great video that Adam Koloff and Brian Buckenberger, I never can quite get it right, did the drone video a couple of months ago out at the observatory. And then we're going to talk about the Mars Ingenuity helicopter flight. And then our program is Dr. Melissa Trainer, and she's going to be talking about the Dragonfly mission to Saturn's moon Titan. Next one here, Mr. Here's our program events coming up this next Friday, week from today, is our guest night. We've already had about 6 or 7 groups of individuals, families sign up, and we'll probably get some more over the week to come out to the observatory. And we're going to try, since the sunset's late, we're going to try to start the primary night on Friday. That way, if we get clouded out on a Friday, we still got a Saturday as a backup night, which we used last month. We got kind of clouded out and stormed out on the Friday for our members' night. We had a beautiful night on Saturday night. Our members' night's going to be the 27th, same way. If it's cloudy, we'll do it on 28th. And then we have a couple of them coming up in June on the 17th and the 24th. So we're going to need some volunteers to help us on the guest nights. Essentially, you just kind of come, set up the telescope, or greet the guests, kind of help them get from the parking lot to where we're going to be. So we'll be glad for you to help sign up. Mr. Don, that helps you sign in a while ago. Don Bradford is the one that kind of works with the volunteers. There's the times on the eclipse. We'll look at it a little more closely later, but it's going to come up in the southeast, and the total eclipse runs from about 10:29 until just before midnight. Okay, next one. A couple of things coming up this summer. If you want to go to some astronomy events where you get to meet other astronomers throughout the country, the Mid-States region is Oklahoma, Arkansas, Nebraska, Kansas. Mid-States region of the Astronomical Union. They're having their meeting this year in St. Louis, and my wife and I are going to go to that one and see what some of the other clubs are doing. And I've been to 5 or 6 of them. They're always fun to go to. They have some neat speakers, and they have door prizes, and all sorts of nice things. And first night's going to be out at the observatory about 40 miles south of St. Louis. So that'll be interesting. The National Convention is going to actually be in Albuquerque this year. They tried the last 2 years to have it there. Last year, they had it on virtual Zoom meetings, and we could all watch in. I watched several of the sessions. They were quite interesting. You go back to our, it's either August or September newsletter, you can see links to several of the speakers' talks. They're very good. It's going to be in Albuquerque. One of the side trips is a trip up to the Very Large Array, which is a radio telescope thing that's, I've forgotten how many antennae there are. Each of them is 81 feet across, and if it's spread out full length, one end would sit in Owasso, one end would sit down southeast west of Jinx, and the other one would probably Greater Coweta. It's really big radio display. I've been there once. It's up on a high plane, about 7,000 feet. So they've got some other things going on too. Okay, next one. So this is our total eclipse. How many of you have seen an eclipse of the moon? Most of you have, but if you haven't, you don't have to have any special equipment to see it. You can simply go out and watch with your unaided eye, or if you got binoculars, that helps a little bit, or a low power telescope. Don't need any super duper telescope to see the moon. It's a full moon. It's going to come up in southeast, and first thing it goes into is the Earth's outer shadow called the penumbra, where if you were on the moon, you see part of the sun peeking out over the edge of the Earth. As it sinks deeper and deeper into the penumbra, that one side of the moon kind of looks like it needs a shave. It kind of gets kind of darkish gray. And then finally, when the total eclipse, partial part of it starts, the part of the moon will look like there's a little bite out of one side. And if my computer simulation was right, it would start like a little nibble about the 7 o'clock position on the moon and slide across over about an hour. And then the moon will be completely inside the Earth's shadow. Aristotle argued that the Earth had to be round because every time you see a lunar eclipse, the shadow on the moon is always curved, and they happen at different times of the year. So it's a long total eclipse, 84 minutes, and the color of the eclipse depends on the amount of dust and everything in the upper atmosphere. It's essentially the light being refracted around the corners of the Earth, so you see all the combined light of the sunsets and sunrises around the Earth. And I've seen one that was almost new copper penny orange. I saw one that just when my son was born in '82 that was deep, rich red. And I don't remember a year, but there was one year there had been a volcano in Mexico, and you couldn't see the moon unless you had binoculars. It was just almost shaded out. Is it possible to pull that up on the dome?
That's what I was doing. So you have to ignore that big massive screen for the projector. And for those of you on Zoom, there's no way for me to project my dome, so unfortunately you're not going to see this next part. But this is the exact kind of format I did it with my students, that on 5:15, starting at 9:15, if you look to the east-southeast sky, where my laser go? Here it is. If you look to the south-southeast sky, or east-southeast sky rather, you have right here, the moon is going to be coming up, and that's just starting the penumbra. So actually, let me center up the moon. Yeah, it's going to be actually not the greatest to center it because of that big screen there. Let me zoom in a bit. That'll help it. You can barely see the circle. It's not the brightest thing, and I can't change the color. I wish I could, but it's this red circle there. That's marking the penumbra. And then the umbra shadows this inner circle right here. So this is showing pretty much the start of the actual visible part when the moon is entering the umbra shadow. And then if I go ahead and advance through time here, you can see it's going to fade into that. Oh, that's just the stadium lights in the way. You can see now it's entering that circle right there is the edge of the circle. And so it's entering into the eclipse at that point. Totality begins right around 10:30. And now we're in totality. It'll get the deep red color as it continues near the center. So that's about 11. This is the time I told most of my students, 11 o'clock is about when you want to start watching. 11, 11:30. Oh, it's also cool when it enters. But if you want to see the red, then it's 11 o'clock. And then as it exits around midnight, as it drifts through as it comes out of the umbra shadow of the earth.
Very good. You can gather up your neighbors and your grandkids and watch the eclipse of the moon. As you can see, it's going to take several hours.
Yep. Yeah, so my recommendation is always, as it's entering the circle, right before totality, that's probably the coolest part. So maybe start around 10:15, 10:30, and watch it into 11. That's probably the best part to watch.
I always recommend people go find the moon before it gets into totality.
Yes.
Because sometimes it can get pretty dim if you're not familiar with where the moon might be. You might not find it. And you can take pictures of it with your phone, or you have to hold it still, but you can try getting pictures of it. Anyway.
Incoming screen.
That's coming up this Sunday. So looks like for what the weather report I got says it's going to be clear on Sunday. You can bake that and $5 and get you a cup of coffee, and you believe the Oklahoma weather reports. What we got next? Mr. Brad, your turn. Where you at?
Okay, just to add a couple of things if you want to get really professional about it or whatever, or maybe a little overboard on the total eclipse, you can report what you think the shading is this time using the Danjon scale. I don't have anything to present for that, but you can probably look it up. That's a report on what the color is, basically. I think Danjon 0 is where it's dark, where you can't even see the moon, up to 5, where it's kind of a penny hue. And there's also Fred Espinac, who does a lot of the eclipse work, has asked people to time when the edge of the shadow passes major craters. They're still refining the moon's orbit, believe it or not, and they can use that data to do that. So if you're interested in doing some side projects, that probably estimating the brightness of the moon or the color of the moon is fairly easy, just naked eye type of a thing. If you want to time the craters, when the shadow passes across the craters, you probably need at least a small telescope, and of course you'll need to know what time it is. And next slide. Oh, so we're doing the full. Okay. This wasn't what I was expecting, but I think we can go ahead and do it. We're going to plan on having observing session number 1. That will be how the sky works. The location is probably going to be at Mounds. I don't think it can be at the planetarium at this point. And the date will be announced. We'll sign up. I'll send out an email and get everybody to sign up for that via that email notification. And what you can do in the meantime, or after you've signed up for it, is get your questions together as far as what you want to know about how the sky works. There are plenty of videos on YouTube and such that can help you look at that, or if you have a planetarium program for your phone or for your computer, you can walk through that. And one thing you might want to do at the session is either bring a star chart or a planisphere. If you don't know what a planisphere is, it's a little cardboard model of the sky, and you can change how the sky looks on it due to the different dates and times. That's something else you can get, I'm sure, on Amazon or through skyandtelescope.com or something like that. Okay? Some other additional observing activities. We have an extragalactic supernova named SN2022 HRS that's real near M60. M60 is, if you look at the picture on the right of the text, M60 is the bright elliptical galaxy in the picture. And then the galaxy that the supernova is actually located in is the dimmer, you only see the nucleus down there. Thank you. And then the bright star in between them, right up a little bit, that's the supernova. At least it was the other day when I took this picture. The last time that we looked at it visually was last Saturday night, I think it was, and it was still 12th magnitude like this and fairly easy to pick out from the two galaxies. So finding M60 is pretty easy. There's an article available online that I wrote. Right now, I don't have a way of telling you how to get to that, but if you're interested, you can contact me. But basically, if you look at M60, you're going to see this site, and you can tell that the supernova is there because it's the only star between the two galaxies. I think we covered the lunar eclipse. Unless anybody has any questions about the lunar eclipse, don't wait till Sunday night to ask. Okay. Astronomical League observing programs, there's still one going on. You can see whoever's got the laser pointer, if you point at the certificate over there, that's the thing you get if you do it. It's still online on their observing program website. And what it amounts to is you look at 12 of the brightest galaxies, either image them or look at them visually and sketch them, send in your stuff, and you get the certificate. That only runs till June 30th, so you have a little while longer to do it, but don't wait too long. And then the next thing is going to be the Globular Cluster Season Challenge. Again, you can do it visually or imaging. I'm not sure if it'll be 12 or what the number is yet because they haven't published it. You can't start that till July 1st, and you have to finish by September 30th. If you think about it, that's a good time for globular clusters because they're all pretty much around Sagittarius and Ophiuchus, or however it's pronounced, and you'll want to look in that area, so that's a good time of year for it. John already mentioned Alcon. Okie-Tex is also coming up. For those of you that aren't familiar with it, Okie-Tex is out in the Oklahoma Panhandle. A lot of people from our club go there, good dark skies, some of the darkest in America. That'll be in late September, if I remember right. QPAC is a thing that I've started that hasn't gone as far as I would like it to go, but if we could go to the next slide. I'm sorry, this slide, this is out of order too. There we go, thank you. Tulsa Perth Astronomy Collaboration. I made some inroads with the people at the Perth Astronomy Club. They have fairly large telescopes there that you can link to through Skynet. And some of the things that I've been doing with that is imaging a lot of variable stars, and also on occasion checking out some satellites, or in this case, the booster rocket that sent Chang'e 4 to the moon for China. Chang'e 4 was a lander that is there and is working, but it had a booster rocket that got it there, and you can still see it barely. It's tumbling at about magnitude 17 or 18. Thank you. Yeah, it's kind of hard to see here because it's tumbling and kind of grainy because this is kind of pushing the limit of what that scope can do. This was 6 images at 90 seconds with no filter. It was humanity's first soft landing on the far side of the moon back on 3rd of January 2019. And of course, it was named after the Chinese moon goddess, which makes sense. But this is some of the stuff I've been doing with the Perth telescope, and it's certainly open to anyone that's interested. Just let me know. And then if you could go back a slide, this was the last light curve I got on that supernova. This was back about a week ago, I think. Actually, it says at the top until May 4th. It's kind of hard to read, I'm sure, for everybody, but what it amounts to is it was still brightening, although now it looks like it's leveled off a little bit. All those colored dots are the different filters and basically colors of light that it was imaged in. And then the crosses are my own personal reports, where there's just a single cross that was a visual report, like the one that we all got, those of us who saw it last Saturday night. I went ahead and turned that in for all of us, I guess you'd say. So it's still running about 12th magnitude. If you have a fairly decent sized telescope or imaging equipment or access to remote imaging equipment, you can still see the supernova. And I guess 2 slides on. This is the rocket we were just talking about. That image, the piece that we were imaging was just stage 3, and I'm not real good with PowerPoint, so I don't know how to insert a lot of things, but I can put a white text box on there and show you that that's the part we were looking at. All the rest of it is somewhere else. The fairing was disposed of, and the lander, of course, is on the moon, and the rest of the rockets are all somewhere else too. And then if you look at the other picture there, Earth is the tiny dot, which you may not be able to see, thank you. And the rocket was at approximately that position in its orbit, about 600,000 kilometers from Earth at the time of that image. So the rocket itself goes out further than the moon for reasons that are rocket science, so I won't get into them right now. But you can see these things if you know where to look, know where to find the information and all that stuff, and have equipment you can get to or use. Next slide. Another idea that's come up that I think we're going to try to work on and see if we can work it out is to have a who's list. We had a couple of visitors who came in tonight, and I was able to explain to them and point out a couple of people who were here. What we were thinking of, this was actually a suggestion from Dana. Is Dana here? Doesn't look like it. So I'll blame him or give him credit depending on how it turns out. And that is to have some sort of handout, to have it at our meetings or star parties that kind of give you a list and maybe a picture of John and say, that's the president, me, say I'm the observing chairman, that sort of thing. So you'll know who to talk to about things and know who you're talking to, essentially. So if you have a question about how to join the club, you'll know who to go to. If you have a question about, well, I want to get on your Facebook page, you'll want to talk to Adam about that. We'll have that contact information. So we're going to try to work that out and get that ready at some point, probably be, at least for the indoor meetings, obviously, it'll be in the fall. And I think that's all my part. Yeah.
Well, this came up after I sent out the newsletter. Guy Otwell, I used to make it this big book, bigger than a regular paper, and had lots and lots of pictures, tables, diagrams, all sorts of events, major and minor meteor showers, of course, eclipses, all of that kind of stuff. And I used to buy it, but it was lots of fun to read, but it was kind of oversized to be taken out in the field. But I got an ad or an email that said that they're now going to make a digital version of it. And it's going to be available for $12. Just download it to your computer, or it's 100 and some odd pages, 137 pages of ebook. So anyway, I thought I'd let you know about that, and you can just Google his name, Guy Otwell, and 2022 astronomical calendar, and it will come up. But it was especially when I was new to the hobby and didn't know a lot, it was a good resource to find out information. Did you ever use that, Brad?
I downloaded this. I used to buy a book all the time. I downloaded this, and it's just as good as the book, but it has the convenience of not being a big multi-book.
That's good. So I thought I'd let us know about it, and I'll try to put it in the next newsletter. But for those of you here tonight, you can look it up. Obviously, that's an old picture from the 80s. But, anyway, all right, next one here. Well, I talked about volunteers. Oh, Don, where are you at? There he is back there in back. Don was the person that helped us sign in people. And there's always opportunities for volunteers to help. There in the middle, we have a group of people at our guest night, and we usually set up, 4 or 5 telescopes and show some of them how to use the telescopes and binoculars, and some of them really get into it, especially some of the kids. As long as you show them how it works, they'll start finding things on their own. And so of course, our club members bring telescopes to let people look in. So that's one of the things we need. Don usually helps with the telescope up in the dome, but he always needs somebody else up there with him. We usually take up a group of 12 to 15 people at a time, let them see a few things. Over there on one side, we had an event out at the Botanical Garden. So there's Ben and Jack and myself. And over here on this side was something we had February early March at Oxley Nature Center. We had 100 people show up at Oxley Nature Center. We had one Wednesday night out at Post Oak Lodge. A tour group came from Virginia all the way out here to see the Western culture, and we set up some telescopes for them. So we're going to see a video that they made of an observatory, and that's one of the shots there. So when we were out there, end of August, Brian Wattenbarger and Adam Koloff, Brian brought a really nice drone, and Adam did lots of still shots, and then Adam put together a wonderful video. When we get toward the end of this thing, Dan, stop it right at the end, because I want to show them something there, but go ahead and see if you can get it to run. Stop it right there, Dan. So for those of you new to the club, we've got 4 new members here. There's our observatory. It's on a hilltop southwest of Mounds, Oklahoma, and about 6.5 miles west of Highway 75. The big building next to us used to be an AT&T long distance microwave exchange building. All the telephone calls would come in there. There were banks and banks with switches, and they would get channeled out all over this end of the country. Back during the Desert Storm, the first Gulf War, we couldn't go up there because they stationed some Marines up there. Was a strategic location. What I wanted you to see, and those of you who've been out there, as we come up the hill to our road, we can see on either side that they put in a pipeline about 2.5, 3 years ago. All we see is a little cleared area, but look at that thing. It goes from, Drumright, the refineries, all the way to Memphis. But, having a drone up there at an elevated elevation lets you see the layout of the land, which is going to come up important in our next little video thing. So, all right, thank you, Dan. This is the little Mars Ingenuity helicopter. And the Perseverance Mars rover landed last early 2021, I think it was February. It carried along with it a little tiny drone helicopter. The blades had to spin super fast because Mars' atmosphere is so thin. And it was planned to just be an experiment. Let's see if we can do it. And they said, we're going to plan 5 flights over 30 days. And the first one, it just kind of went up, set back down. But since then, it's become an integral part of the mission. It's completed 27 flights now, covered 7 kilometers or more. So I'm not familiar with distances from Jinx, but from here to Sapulpa, if you're used to going to our observatory from the old Highway 75 all the way up the hill is about 4 miles. So it's gone quite a ways in that time, and it's semi-intelligent. It can go up, and as it's coming back down, it can look at what's on the ground underneath it and decide where to land and all that sort of thing. And so what they've been doing with it is just what I showed you in that last slide. The rover can only see what's at ground level. They can get up several meters and look over the hill and see which way they want to go. Is there an interesting boulder? Is there a place we want to avoid? But on May 3rd, it went silent. The temperatures at night now, winter is coming up on that part of Mars, and temperature dropped to minus 68 degrees below zero. And the thing went into a safe mode. And so to preserve its critical instruments, even the clock was shut off. And so they stopped the whole rover and said, don't do anything else. Just sit here and wait for it to phone home. And sure enough, when the sun came back up and it charged up a little bit, it did finally phone home, but it's probably, as the winter proceeds, it's going to get colder and colder, and dust is always a problem on solar-powered things. But we'll let Dan show you a little video if it'll work. And note where it takes off and then where it lands. It takes off here on the left side of the screen. Goes up and hovers, takes the image of where it started from, then it goes over the hill. What's on the other side of this mountain here? It's not a mountain, but takes a look to see if there's a bear on the other side of the mountain. And it'll be back here. Here it comes back. Most of the flights are 2.5, 3 minutes. But you see it's coming down, there's a boulder there. It's like, okay, I can't land there. I got to avoid that. finds him a nice smooth spot, and down it comes. So that's been a very promising addition to our Mars missions. We can look around and see where we want to go. So that's a little Ingenuity spacecraft. Which brings up our featured program. I've forgotten the year now, 2004, I believe, but somebody can probably correct me. We had the Cassini mission to Mars. No, that's wrong, to Saturn. The Cassini mission to Saturn. And along with it was a Huygens probe that parachuted a probe onto the surface of Saturn's biggest moon, Titan. We knew from the Voyager missions in the 70s that Titan had an atmosphere. And subsequently, we were able to figure out that the atmosphere is mostly nitrogen, like ours, but it also has methane in it. We know methane better as our natural gas. It's 1 carbon and 4 hydrogens. It had methane in its atmosphere. It was too dense for the Voyagers to see through. So the Huygens probe parachuted down, and I was watching the thing live with my students, and came through, and the atmosphere cleared. There below us was a seashore sort of thing with riverlets flowing into it. It just was amazing to see that. But the riverlets are liquid nitrogen, not nitrogen, methane, liquid methane, liquefied natural gas. And so it landed, and of course it couldn't go anywhere, but we want to go back. We had radar missions that mapped pools and lakes on the Titan as it Cassini continues its mission. But the proposal is to send a drone-like device, just like the thing on Mars, but this thing will have to be much more intelligent, and it'll have to be powered by nuclear power and be able to survive the temperatures that are really, really cold there. So our guest speaker tonight is going to tell us about that.
Why we don't have some. The mission and the science that we're going to learn from it. I do want to remind the audience to ask your questions in the chat at sagannet.org or on the NASA Astrobiology Facebook page. We'll get those into the queue then for Dr. Trainer after she and I have a small conversation here first. And Dr. Trainer, I always love with our guests, since a lot of our audience are undergraduate, maybe high school students, maybe recent graduates, they want to know how to become astrobiologists, what our pathways are to get to where we are in our careers. And so I'm wondering if you can share with us maybe your science story, your superhero science origin story for what really brought you to where you are currently in your career.
Sure, happy to. So it wasn't a plan, I should say. I wasn't one of those kids who said, I'm going to work at NASA someday. I love NASA and love planets, but probably like a lot of young people, maybe especially in the 80s, I was mostly only aware of astronauts and the space shuttle program. And that probably made the biggest impact on me when I was a kid. But I always loved math and I love science. And so I followed those interests. For example, through college, I majored in chemistry, partly because I also loved being in the laboratory and I loved like mixing things up. And so as beautiful as the night sky is, I was really a lot more drawn to hands-on laboratory work than necessarily observational astronomy, for example. So I was graduating chemistry. I knew I didn't want to get a job yet. I knew I wanted to keep going to school. And so I started trying to figure out what kind of research really interested me and really excited me for going to graduate school. And I ended up really drawn to the study of atmosphere and atmospheric chemistry, but more so for Earth, right? That was my original thought. I had these like visions of how to climb mountains and measure ozone and do all those kind of measurements. And so that brought me to the grad program I went to, which was at the University of Colorado Boulder. But when I started looking for projects and people I wanted to work with, the professor and the group I was most drawn to, the available project that also really suited, I thought, my interests and my strengths was studying the chemistry, not of the Earth's atmosphere, but of Titan's atmosphere. So sort of a little bit of a just grabbing an opportunity that I had to do something I hadn't necessarily planned on, but still found really interesting. And that's sort of the theme when I think about how I got to where I am today. That's sort of the theme. So I did all my graduate thesis work studying Titan as well as the early Earth and kind of the connections in atmospheric synthesis and the role that might play in distributing complex organics kind of all around the planetary system. And I did a little postdoc work studying Mars polar caps, and that was right around the time that methane observations of Mars were just starting. There was a lot of interest in that. So again, just tried to do some lab work, thinking through what are some possible mechanisms of trapping and re-releasing methane. The spoiler alert is we didn't find any. I didn't find any in that particular project, but sometimes a null result is still really, really valuable. And then we're kind of ready for the next step and trying to figure out what I was going to do. And I think I had sort of always assumed I would, go into academia and try to get a professorship. But again, like sort of out of cycle from that, before I could even do all that work, this job opportunity at Goddard popped up, and I ended up meeting with the people who are hiring, coming out to visit, giving a seminar, and it was yet another one of those. This is not necessarily the thing I planned to do, but this is really exciting and this is really interesting, so I'm going to give it a try and see how it goes. And that is how I got to Goddard. And then the group I joined is one that is very involved in missions and in building instrumentation for missions, such as the SAM instrument on Curiosity. And through working in that group and working at an institution especially that's really based in mission work and proposing and executing planetary missions is sort of what led me kind of in the business and set me up to be part of the Dragonfly team.
Oh, that's wonderful. I'm super jealous. It sounds like you've had your hands in so many different awesome missions and concepts as well, including the Titan Mare Explorer and all these things are kind of coming up to this culmination of exploring Titan. One really cool thing I learned from you in preparation for this episode was actually going to lead into our current field site challenge we just released yesterday. On Twitter, we asked people to guess the location of a certain picture relevant to the exploration of Titan. And that picture was an image of linear dunes in the Namib-Sian Sea in Namibia. And I can't help but hear David Attenborough's voice going, the Namib, the way that he would say it so poetically and beautifully when we talk about the Namib. Our winners for that contest are Lloyd Jolly, Cass Marion, Sri Likya Chowdhury, and Eduardo Aco Perez. So thank you to all of you who competed in that challenge as well and realized this was Namibia. And I wonder if you can speak to that, why Namibia is so important for our explorations of Titan.
Sure. So one of the features of Titan that is really fascinating and compelling to think about and is part of our target when we go with Dragonfly are these dune fields, these equatorial dune fields that are present and sort of wrap around the moon. They're really noticeable from the images that we have of the surface from Cassini, and the formation and the processes that lead to those dune fields and kind of the shaping and the spacing with these wide interdune flats where we think we have access to the bedrock, which on Titan would be water ice, as well as then the sort of pileup of dune particles. The way those are formed, we said would be very similar to how some of the dune fields on Earth form. And so that image that you showed and that Namibia sand sea is an analog for that region on Titan. But what's so cool about Titan is that it's totally different materials. I sort of hinted at that already, right? Instead of having your exposed bedrock be some kind of, silica-based rock, it's water ice, which is the crust of Titan. And the dune particles that are piled up are expected to be made up of organic carbon, organic molecules. And exactly how those particles form, we're not entirely sure, but that's part of what we want to learn more about.
That's great, and that leads me then to Dragonfly and learning more about it. So I mentioned earlier, Titan was the first moon of Saturn we found, and we now know of lots more. Titan's surface is very cold. It's like 20 Kelvin warmer than liquid nitrogen, so it's pretty cold. And yeah, there's this methanological cycle instead of a hydrological cycle, and there's methane going to the atmosphere and breaking down and making all these other things through photochemistry, and there's like this raining gunk coming down to the surface of Titan, which is very cool. I wonder if you could then set up for us maybe the brief history of exploration of Titan. I know we had one mission land on Titan, and what really leads us now to want to send Dragonfly there? I've heard this question a lot. Why are we sending Dragonfly to Titan?
Sure. So you've talked a little bit about the original discovery of the moon, just looking from Earth through telescopes, and that's probably just because it's large, right? So it was one of the earlier moons that was able to be observed. And there were studies from more advanced studies earlier last century using telescopes that led to the discovery that Titan has an atmosphere, and in particular that there's methane in the atmosphere. And so that sort of already kind of pulls Titan out as unique among all the other moons in that it has a substantial atmosphere at all. And then with flybys from, for example, Voyager, we got some really good images of what Titan looks like kind of from the outside in the visible. It's like this hazy orange ball. It looks kind of like a marble or like this fuzzy ball. But spectroscopically, we see that's related to, as you said, the methane in the atmosphere, but energy coming into the atmosphere and photolyzing that methane leads to very complex chemistry. And so the particulates that give it that hazy orange look, and that right there is sort of the first clue. Titan's got something really interesting going on. These are organic particulates made up of chemicals that are formed through that process, and they condense out and they make this haze, and that completely obscured the view of the surface. But it was the first hint that there's some really, really interesting carbon cycling going on, and the potential for those organics to be very complex organic species. So it wasn't until we got there with Cassini, the Cassini-Huygens mission, that we were able to actually see through that haze layer and get an idea of what the surface was like. Before that, there were a couple different hypotheses. One was that maybe the surface was covered in just a whole ocean of liquid ethane, with the thought that ethane would be a major product from the photolysis. You get enough of it, it's all going to just condense out, and maybe there's liquid ethane everywhere. They're not totally sure until we got there with Cassini-Huygens. And so Cassini was the Saturn orbiter. They dropped the Huygens probe off. Huygens fell through the atmosphere for several hours, and then it lived on the surface, actually, which wasn't necessarily expected or planned for because we didn't know what it would land on. But it survived on the surface for about 70 minutes. But what it did while it fell through the atmosphere, it took images of the surface, and as it descended down from those images, we could see sort of evidence of really interesting topography, river channels. It landed in what looks like a plains, sort of a plains area. And it also took measurements of the composition of the atmosphere while it fell down, so the methane and the nitrogen, as well as some of the trace species and isotopic ratios of some of the major species, and also things like pressure and temperature, kind of giving us the profile, winds, all the way down. So that's sort of our one point, data point of really understanding what Titan was like all the way down to the surface. Also looking back up at the haze, at all those particles, to get an idea of sort of what are they made of, what shape they are, how dense are they down to the surface. And then since it survived on the surface, we have really great images taken from Huygens sitting of what that area of the Titan surface looks like. So those 3 hours was an immense leap in our understanding of what Titan's like. But luckily, Cassini kept coming by Titan over and over, right? So over 100 flybys of Titan. And from that, we have learned so much too about Titan, as a planetary system, basically, right? As I always refer to it often as a planet, because other than the fact that it orbits around a different planet, it acts like a planet. So the Cassini orbiter gave us views of the surface in different, channels of light that could get through the haze, the absorption of the methane or the haze, different visible and infrared lines, as well as using radar to get ideas about the topography, what the surface is like. And from that, we can see, Titan is a fascinating place. You've already hinted at a lot of the cool features, things like the methane cycle that acts like the hydrological cycle on Earth. We have observed clouds. We've seen evidence that it does rain, sometimes on Titan, except there's river channels. Cassini discovered near the North Pole a whole region of seas that are primarily methane and ethane seas. So Titan's the only place in the solar system you could go sailing other than Earth, if you could stay in the cold.
That's awesome.
And there's, we mentioned mountains. It's been speculated that there might be cryovolcanism. So the ice shell acts sort of like bedrock does on Earth. And then for Titan, underneath that, there's a subsurface liquid water ocean. And so it's thought that it's possible that you could get eruptions of this liquid water out onto the surface. And despite the fact that Titan is so cold at the surface, if you have enough energy, either in that kind of eruption of cryolava, or, for example, a big impactor comes in, it's a big impact crater, you have energy in the system, and you melt the water, you have some liquid water present on the surface, it could last for 100, 1,000, maybe even 10,000 years, depending on how much energy it takes. It still takes a long time to cool off. And so when you put this all together, what we've learned from exploring Titan is that you've got this location where we have sunlight coming in, potentially other energy sources. We have water, definitely liquid water below the surface and sometimes on the surface, and we have more organic carbon than you could possibly need, right? It's sort of the opposite of what we're doing on Mars, where we're looking for just a few molecules preserved in rocks, right? And Titan, it's like it's organic carbon everywhere. We have complex organics. So what happens, right, when you have all of those things together? So what happens when you've got this super rich organic chemistry taking place in the atmosphere, and it's depositing everywhere, it's depositing all over the surface. You suddenly have an impactor come in, you create a melt pool. Now we have all this organic molecules, and they're sitting in water, and they're sitting in there for thousands of years. You have a lot of hydrolysis reactions, other reactions can take place. You start to make the types of molecules that we think of as important for biochemistry. You start to make things like amino acids and nucleobases. And if you are able to make them in the synthesis step, do they continue going on? Do you make any oligomers of those things? What kind of how far can abiotic synthesis or this kind of process take you in terms of complex chemistry, sort of on the route, like what we think of as prebiotic chemistry? So those are some of the big questions that are part of the Dragonfly mission. Those are the big questions I have in going to Titan and exploring Titan. And then in addition, we're able to make like very specific measurements, maybe about some of the chemical composition of some of the surface materials that we encounter, but we can do so putting it in the context of the whole area that we're exploring in, right? So also spending time on the surface and making measurements, understanding the environment, understanding sort of the meteorology, and kind of piecing it all together, what does it mean to have a place like Titan that has all the ingredients we think of are important for life? And how does it all kind of come together as a system? And what can we say about what that means for what we think about habitability? What makes a place habitable, for example?
Interesting, yeah. So it seems like there's a lot to learn just about planetary processes in general and atmospheric processes by going to Titan and exploring. I've not read before about the potential for liquid water to come up to the surface or an impactor to leave it on the surface for a long period of time. So that presents a really interesting potential for an oasis or a refuge, if you will, for a potential life if it's there. So how would Dragonfly then specifically as a mission help us to understand this? What kinds of instruments will we be taking? What kinds of measurements will it give us?
Yeah, so one of the big features, and I'm gonna point to the Dragonfly in my, since I'm broadcasting from Titan. Of course, one of the key features of Dragonfly is that it can go to more than one location. So we call it a relocatable lander. So we're able to visit multiple types of locations. I've talked about dunes and organic dune fields, and now I've talked about this potential for there to be, we know there are impact craters, and that at some point in their history, they would have been liquid water, frozen over now, but our plan is to visit one of these impact craters and look for evidence of this type of chemistry. So the way that we'll do that, we'll measure the composition of the surface in several locations and be able to compare it and kind of understanding a process in history. We do that a lot of the way, very similar to how Curiosity rover makes similar measurements on Mars and looks for organic materials on Mars. So we'll drill into the surface. We have a cryogenic drill, and that delivers the sample to a mass spectrometer. So using the mass spectrometer, we'll look for different types of organic molecules, identify different compound classes by comparing like what we find in the dune sands to what we might find in sort of this frozen over impact deposits. We can make some inferences again about the type of processing that may have taken place. We have two different ways to measure surface samples with the mass spectrometer. One involves shooting them with the laser, which is sort of our first look, and that helps us get some of the larger molecular weight molecules. Then we also have a gas chromatograph, and using that approach, and again, this is something that has been done on Mars, we do what's called derivatization. So we use a chemical reagent and mix it with some of the molecules that normally might not, if you heated them, go into a gas flow. We make them more volatile, and then we can send them through our system and measure them in the mass spec, and that includes things like amino acids. And it also gives us the capability, we're carrying a special separation column with our gas chromatograph that lets us look at chirality. So that's sort of the handedness of molecules. That's really, really important biosignature for our biochemistry as we know it on Earth. And so that's something that we have the ability to look and see if there's a big enhancement in one chirality or another. So that's very focused on just, the chemistry measurements. But we're making tons of other measurements as well. Again, to really understand this whole planetary system and learn more about planetary processes as well, and put the chemical measurements in context. So, of course, imaging, lots and lots of imaging, right? We couldn't go to Titan and fly around Titan without sending back lots of pictures. So we have a whole suite of cameras that lets us get panoramic views of where we're landed, forward and down-looking views. We have a microscopic imager that'll let us see in much finer detail the types of surfaces, the types of materials that are there, including the area where we will drill if we decide to take a drill sample. And so from piecing together all of those, we can learn a lot about the geologic history of the different landing sites that we're in. For example, to learn a lot more about how those dune fields are formed and transformed over time. We're also making meteorological measurements, so things like temperature, pressure, wind, looking at methane, humidity. We have the ability to make seismic measurements, a seismometer, for example, to learn more about the interior and try to constrain the distance maybe from the ice crust down to that subsurface ocean, and understand a little bit more about interior structure and how that interior might connect with the surface and what implications that could have for were there, let's say, potential life in that deep subsurface ocean. We also have gamma ray neutron spectrometry measurements, which are which are really useful. We are able to get a bulk elemental composition of every landing site that we're at. So it sort of tells us, what major elements, of course, carbon and hydrogen and oxygen will be important ones as we're landing on sites that have different amounts of water ice or maybe organic molecules sort of layered on top, almost like a soil or layering on top. But if we land in an icy spot, we might also see evidence that there's a lot of salts, chlorine and sodium and different cations and anions. If they kind of pop up in those measurements too, that could tell us a lot about the history of that area and, again, potential connection maybe from the interior ocean. And that also helps us classify site to site. Is where we're sitting now very similar to where we were last time? And if so, do we want to, is it worth drilling and taking another sample, or should we keep continuing on to find kind of a new geologic unit?
So very cool. I'm just like smiling widely over here, just thinking about Dragonfly and what's possible. I do have a couple of rapid fire questions for you actually too. I gave a talk last week at the Denver Museum of Nature and Science, and of course, children always ask the best questions. And I had a bunch of kids ask questions that I had no answers to. So a quick one, how big is Dragonfly going to be?
Okay, so Dragonfly, you want to picture the scale is kind of like a Mars rover, right? So this is not a teeny little drone. This is a serious spacecraft, because it's got to carry that whole payload.
Okay, so I mean like a small, like a Mini Cooper kind of size?
Yeah, something like that. Maybe, I mean, it'll have its own little dimensions, but, it's, hundreds of kilograms.
Very cool. Another question that I had, why did we choose to put on 8 propellers on the spacecraft? Why not 4 or just 2?
Well, by having 8 and having them arranged the way we have them, where it's really 4 locations with 2 each, that gives us a little bit of redundancy. So if one of those rotors were to go out, for example, we could keep flying. We keep flying it in a very balanced and controlled way.
Oh, very cool. Then another question. So obviously there'll be a nuclear fuel source for powering the spacecraft, or for powering the craft on Titan. But how long do we expect it might live? What's the optimal time for the mission as of now?
So the plan is to use an MMRTG, right? So that's how we propose, and that's what the architecture is dependent on. And it will depend right now based on the cruise time that we're looking at. And we land, and we have a 3-year prime mission, right? And throughout that whole prime mission, we have enough power, certainly, to do everything that we need to do. But we should keep getting enough energy out of the power source to keep going. And then over time, ultimately, it will start to degrade. But, we're looking at several years on the surface of Titan, hopefully beyond the prime mission even.
Yeah, I mean, we're still learning, right, what we can do with these nuclear sources for spacecraft on planetary surfaces. Obviously, with the Voyager spacecraft, they've been going for decades now, using a nuclear fuel source. And so it'd be cool if it could last for that long and really give us many years of measurements from the surface of Titan, and lots of really cool pictures and lots of really cool chemistry for all of us back here. I do want to change topics just a little bit. Before that, though, just remember for the audience, you can ask questions right now in SeganNet's chat feature at segannet.org or on the NASA Astrobiology Facebook page. I see questions coming in right now for Dr. Traynor, and so I'll get to your questions here very soon. But a few other questions I have first. So you've done a lot of other work, not just looking at Titan and its atmospheric chemistry and some of these things. You've also been involved with the SAM instrument on Curiosity, and you mentioned earlier like methane detections on Mars. I remember when those first started coming out, like Mike Mama was using a telescope here at Earth and looking at Mars and seeing methane, and a lot of people didn't believe it. I was skeptical of methane on Mars at first as well, but now we've had repeat measurements. But recently, you were also involved in an announcement of finding oxygen on Mars. And I wonder if you could just tell our audience about that detection and what we think might be going on to be putting both methane and oxygen potentially into Mars's atmosphere.
Sure. So we expected to find oxygen. Oxygen was measured certainly by the Viking landers as well as other spacecraft or other observations of Mars. So we knew that oxygen was there. What we were able to see with the SAM measurements that couldn't be seen before was how it changed over time, seasonally, and how it changed compared to the other major gases in the atmosphere. So with the SAM instrument on Curiosity, we've been on Mars for over 8 years. I have to pause because my daughter was born right after we landed, so I can always remember how long we've been there, not how old she is. We've been on the surface for a long time. We're not making daily measurements of the atmosphere with the mass spectrometer, but we're making frequent measurements, and we were able to kind of build up over time coverage that then spanned all the seasons and had lots of points over repeated Mars years. And that was a big first, right? So all the other measurements have either been observations, from orbit or from telescope, or for example, the Viking landers, which made that kind of comprehensive measurement of all the composition of the atmosphere, but only for a few sols, only for a few Mars days. So we sort of built up this first data set, and things like argon and nitrogen, which we know are inert. They don't chemically react to other species. They don't really interact very much with the surface. They behave very well. It's a weird way to anthropomorphize them, but they have a very repeated cycle that we expected to see. And every year, we could fill in the points, and it would make this, put together this nice curve. But the oxygen was not following the same patterns. It would rise a lot earlier in the spring than the argon and nitrogen, and then it would kind of drop down really fast. And both of those aspects of the oxygen cycle were unexpected. Based on what we know about oxygen photochemistry and the cycles in the atmosphere, you would expect it to actually mostly look like argon, behave like argon. So it tells us whenever we get to make a measurement that hasn't been made before, hasn't been made with the same resolution that it's been made before, and you don't see what you expect, it just means it's time to go back and question the assumptions. So we had an expectation based on only one real process of controlling oxygen in the atmosphere, which relates to photochemistry. And by seeing different behavior, it's telling us there's something else going on. And we don't have an answer yet. So these results took years and years to build up. And we published them about a year ago. And part of the idea was to say, hey, this is an unprecedented data set. This is something interesting and new. And it was a little bit out to the community, the science community, maybe some of the people on this call, see what you can think about. I think that there's probably a really strong connection to the surface, to processes that are going on in the surface, heterogeneous chemistry. There may be a reservoir where oxygen gets converted into another species temporarily, and then it could be re-released. That's one way to potentially explain how it can kind of come out fast and then go back away fast. But we haven't found a smoking gun in terms of what would that reservoir be and what would trigger kind of release or reabsorption. We compared our results to everything else that we were measuring at the time, whether it was UV incidence or temperature, pressure, surface ground temperature, dust loading, the methane you measure. So we compared it as best as we could to the measurements of methane that were made. And the methane and oxygen is interesting. They sometimes follow each other and sometimes not. There's parts of the year where they seem like they might be tracking, and then other parts where they're not. So that seems like another really important clue too.
Interesting. That's really groovy. And so you guys heard it. Dr. Trainer has said it's a challenge. Help us figure out what's going on. Maybe someone listening right now, maybe an undergraduate student or high school student listening right now might be involved in helping us to solve these puzzles. And as always in science, it's not always a case of eureka. It's a case of why is that happening? So Dr. Trainer, before I open it up to our audience questions, I do love for all of our guests just to chat a bit about what it is outside of science that drives your life forward. So you mentioned to me before that you're really into your family life, and you guys have a lot of hobbies together. You like to get outdoors with your family. I wonder if you could just let us know what kinds of adventures have you and your family been on lately?
Sure. Well, this has not been a normal year, as we're in agreement. But we, a few years ago, we got really into trying to visit different national parks. I love the outdoors. I love the natural environment. I probably don't get into it as often as I would like, living in, suburban Washington, D.C. area. But we started trying to visit different national parks. The previous summer, we had gone to Shenandoah. We've been to some in Hawaii, like Haleakala, and I used to live in Colorado, so I've been to many of the parks in Colorado. But now my son, who's 11 now, he's like really into it. He wants to like be able to check some of these places off of his list. So this past summer, we were supposed to go to Yellowstone. We had to curtail those plans, but we decided to stay semi-local, and we made a visit down to Great Smoky Mountain National Park. And that was a first for all of us. It was amazing. It was beautiful. We loved it. We got to see some really cool wildlife, and it's just far away enough from where we are now. We really like birds. My kids like to do. They're not the most patient, quiet bird watchers, but when we do see new birds, we like to figure out what they are and kind of keep track, in a little book. We saw some elk. Again, park elk that were very blasé about the people and could care less about us there, not in any way afraid or interested. So that was really cool. And we also just tried to do, I think like a lot of people, we just tried to do some outdoor activities that seem safe. Given trying to be careful with coronavirus. So we did horseback riding through the forest. I took my son zip lining through the trees, just lots of fun outdoorsy stuff. So a lot of what I do, the adventures I have are different than the ones I had before I had kids, but it's so fun as they get older, we can do more and more. And I can do fun things like zip line by conning my kid into doing it with me.
That's awesome. Yeah, my son's only 16 months old right now, and so I'm at that phase where he can't really do all the cool things I want to go do just yet. But so there is a hope that down the road we'll be doing some zip lining together. I love it. So I'm going to open it up now to the audience Q&A. We have a bunch of questions coming in from the audience. Keep those questions coming, folks. We'll try to get to all of them if we can. The first one is a question that came to us through Twitter from a longtime watcher of the show, Dr. Jim Pass. As an astrosociologist, he says, he's interested in hearing your thoughts about the search for extraterrestrial life and how it affects societies even without ambiguous evidence, and how things might change if we do find such evidence.
Wow. That's a great question. I'm very much out of my expertise, and I'm speaking only, this opinion is only my own type answer. Personally, I think that if we are to discover life off of Earth, whether it's like something that presents itself to us, or something even just as simple as a microbe that we discover on another planet, to me, I'm hoping that would be very unifying for our society. It's a little bit of like the Star Trek view, I think. It really helping us remind ourselves as humans and as Earthlings how we're so much more similar than we are different. And I would like to think that would kind of bring us together as a species on Earth. And I think even for those of us who do search for life off of Earth, we have to think really hard about what could it look like. Should we expect it to be similar to life on Earth? And that already kind of puts you in that mindset and really thinking about what does it mean to be life on Earth? What does it mean to be an Earthling? What does it mean to be a citizen of this planet versus what could it be like for someone on another planet? So that is based on zero research. But my hopes, I think, of why part of why the search for life, I think, is an important endeavor for humanity and makes me hopeful for our society.
That's great. Yeah, I agree. I love that response. And, our questions coming from our audience can be about all kinds of topics that they want to ask an astrobiologist. The next two questions are Titan related, though. So the first is from Andrew Planet. He asked on Twitter, was that very short active lifespan of the Huygens spacecraft intentional? Did they know it was going to last for such a short period of time?
Yes, absolutely. So it was designed to be a descent probe. So the whole mission for that Huygens probe was to fall through the atmosphere, and it did exactly what it was supposed to do. And in fact, the 70 minutes it survived on the surface was complete bonus science. Right, so that wasn't even originally planned because they couldn't guarantee what it would land in. So one thing you learn, what I'm learning, right? So this is the first time I've ever sat on a mission from the conception, all the way through development. And what I'm learning is you want to be really careful. You can't put requirements on the planet. So I can't guarantee Titan is going to cooperate. I can only plan for what I can constrain properly and what I can expect. And then there's some things where you're like, well, if Titan cooperates, we'll get this, or this will happen, but we don't know.
Awesome, yeah, so it could have just like sunk down into a group of hydrocarbons
Exactly,
and that could have been it.
or hit a harder surface than we expected, maybe, and broke something,
Mm-hmm. Oh, interesting. Yeah. So another question from Azul Pinoba on Twitter. Azul wants to know, is it known how Titan's seasons influence the methodological cycle?
It is, yeah. So one thing to keep in mind is that a year on Titan is the same as a year on Saturn, which is about 29 and a half Earth years. So Cassini was able to observe Saturn and Titan kind of going through a big seasonal change, right? But not even a whole year, only a half of a year. And so we were able to make lots of observations with Cassini flybys about how the seasons can shift some of the chemical species. We think it can influence, perhaps there's lakes near the sort of dried out, what look like dried out lake beds that may get filled if there's some rain in other seasons. And then just the rain in general is expected, we can see clouds that formed in sort of certain seasons in certain locations, but then not in others. So there's definitely expected to be an influence. It's very slow moving compared to Earth, not just because of that. Well, there's that long timeline of the seasons, but also because it's very cold. And so in general, the atmosphere is going to be a lot slower and a lot more sluggish than what we experience on Earth, right? The huge temperature gradients you can get from solar insolation on Earth, you're very far out there. The sunlight is going to just influence things in a smaller and slower way. And I should also say it's not just Cassini that helps us observe how Titan is evolving through the seasons. Of course, there's still ground-based or other space telescope measurements that can be made as well that help us track out those things. And so I would say I think we have a beginning understanding of how that works, and that's supported. Ongoing work on that also gets supported by models that we can do, sort of global circulation models that help us try to understand it and match the data. But with Dragonfly sort of will be a ground truth for at least this one area of Titan, making observations and will really help us understand that even better.
And that's a great point too, actually. There's another question right now from Aniruddha Hampi at Strayologist on Twitter. He wants to know about the landing site selection, which we didn't even talk about yet. It says for NASA's Perseverance rover, we used remote sensing data of Mars to select a site of scientific interest, but also, the engineering had to allow us to actually have a landing site. So can you speak to what we currently have for a landing site for Dragonfly and how we selected it?
Sure, absolutely. So we have all the data that was accumulated from Cassini. So I mentioned sort of between the visual spectroscopy and radar data, we actually have a good set, and we picked locations on Titan where there was a good data coverage, so that we had the best data that we could have about what the surface was like. We have what we know from the Huygens probe coming in and taking up close images of the surface. And then we took that information, and then we also thought about, well, what do we want the mission to do, right? One of the biggest goals is to visit more than one type of compositional area. So one thing that we can see with the measurements we've been able to make of the whole Titan globe is we can't tell exactly what the surface composition is in every location, but we can classify it, right? So we can classify, there's sort of like these dark areas, and then there's we got like blue areas where we know there's water ice included. and maybe some brownish or greenish, just kind of classifying it all and looking at that, you can see how diverse the surface is. And so I talked a little bit about dunes and I talked about impact craters. So in addition to being, topographically diverse, geographically diverse, these are also chemically diverse areas, right? They have different provenances, so the materials are likely made of different things. And so we wanted to be able to visit as many of those places as possible and to include one of these frozen over impact areas where we know there used to be liquid water. So that sort of gets at our prebiotic chemistry goals. And so we found this location near Selk crater. Selk is a known impact crater, and it's right near this Shangri-La area, right with the dunes. And so by going to this location, we're able to visit the dune fields, understand the organic sands that comprise them, and where they come from, but then also look at an impact crater where there might have been this more advanced synthesis. And the data that we have isn't as high resolution as the type that we have for Mars, certainly especially for, Perseverance. We have very high resolution data for Mars. We have to remember we don't have to drive across the surface. And another cool thing is that when we come in, the craft itself comes out of the back shell and transitions to its own powered flight. And so it can pick its landing site, its initial landing site, and it does so using imagery and LiDAR and like terrain navigation to select a safe landing site. So it's okay that we don't know the exact precise, really, really high resolution areas. We know enough to know that there are big flat areas in these dunes and that there's a lot of potential landing sites. And then as we go, we'll always be doing reconnaissance. We call it leapfrog. We'll always be flying over a new area, making really high detail, making our own maps, right? Coming back to the original landing site, deciding where the next target is, and then moving over to that.
Oh, awesome. And you kind of alluded to this earlier a good bit, but Miriam Nassim on SegaNet wants to know, from an astrobiology perspective, if you think Titan may be habitable or could be inhabited, and what kind of life you think might actually be able to survive on Titan.
Yeah, so this is such a fun question. In the subsurface ocean, right, that's often thought about as probably the most likely long-term habitat for life, water-based life, right? Because if it's maintained for a long period of time, and if there's sufficient nutrients and gradients in that location, then that would be the place that would be most likely to harbor life. That's one reason we think about connection between the ocean and the surface as being really critical. But the truth is we don't really know how life evolved on Earth, right? So maybe some of those surface environments, even if they're transient surface environments of liquid water, or if they're fed from the interior, it's possible that life could have at least persisted for brief periods of time in those environments. And I think Graham used the word like refuges or oases maybe. And so maybe they would have been temporary, but 1,000 years doesn't seem temporary to like a bacteria, right? So it doesn't even seem temporary to me. That's a potential. Maybe it was just this very brief amount of time. And then if you want to get really exciting, then we can think about, okay, well, we know there's these methane and ethane seas at the poles. We know there's, maybe methane soaked sands in other places. And then we can start, having fun thinking about like weird life and what potential, other biochemistries could be supported in that type of environment. I know there's some good, some people have started looking into that type of possibility.
So groovy. I remember a few years ago, the folks at Goddard's Visualization Studio released like this video of a submarine going down into one of Titan's lakes and looking around. Made me wonder if there could be some weird alien octopus that lives in methane and ethane lakes and super cold temperatures down there to grab that submarine.
Yeah. I think we all hope if we send a submarine anywhere, whether it's Titan or Europa, I think we all hope it'll get eaten by an octopus.
Exactly, yeah.
Sure,
From Jules Verne, it's just in all of our heads, it's ingrained in the culture of science fiction and all these things. So let's jump ship a little bit. Our next question comes from Blake Overbay on Facebook. Blake is majoring right now in environmental chemistry and has interest in abiogenesis. And origin of life. And so Blake wants to know, and then you may not have the best answer for this. It's up to you how you want to answer it. If astrobiologists right now are trying to answer these questions of the origin of life, is there a lot of call for origin of life research? And do you think that we're getting closer to finding life from non-life?
We're closer than we ever were. That's the best answer I give. No, there's a huge community of people in origin of life research. Absolutely. Luckily, before the shutdown happened, I was able to go in person to a really great meeting on origin of life research earlier this year. And there are so many different ways that question is being approached. It's very multidisciplinary. Philosophically, just, like a wider range of sort of philosophies and how to think about it. We're thinking about what happens if you bring in material from outside to a planet. What happens if the planet sort of makes its own, chemistry, kind of like I've been talking about with like the Titan, like prebiotic chemistry. There's so many different ways to think about it and to understand what are the controlling parameters of an environment. And people are making a ton of progress in understanding sort of what are those first critical steps of synthesis, at least for the early Earth. And so in that case, we have minimal constraints. And so it's good that so many people are kind of approaching it and thinking about it in different ways, because you have to explore all these potential pathways for how it might have happened on Earth. We have very little evidence of what happened back then. All we have is the endpoint, right? The life we see around us. But that's one thing why we think it's so cool to go to Titan too, because that's a place where you don't have life all over everywhere, right? Biology hasn't just overprinted on all of the chemical processes that are going on. And that's part of helping us, ultimately go back and think about what happened on Earth billions of years ago that led to the formation of life there.
Yeah, and I often tell people that there's a good chance we'll never know for sure how life started here on Earth, because we might have lost that record chemically. But with Titan, there's a chance we could actually see the process in action, even if that process does take a very long time. So that's what we'll think about. Another question from another undergraduate, Kennedy Marthaler, has said that they're an undergraduate majoring in physical sciences, math and physics, and are determined to go to graduate school for either astronomy or looking into astrobiology. And they want to know if you have any tips in how to get started in such programs. They are competitive sometimes to get into these programs. And so we can also go a little bit broader if you don't mind. What would your advice be to any of our undergraduates right now who are watching and might be interested in pursuing astrobiology?
Sure. So I'll speak specifically to how I got into astrobiology and what I think was really helpful for me. And what it was to stay in a primary discipline. So instead of pursuing maybe a degree, a PhD that was just astrobiology or what I did is I stuck with chemistry, which I really liked. But that could be physics, it could be geology, it could be any of those things. So I kind of stayed in a core discipline, so more traditional, I should say, is what I'm saying, discipline, and then got involved in taking classes that were related to astrobiology, or having research or participating in meetings and seminars that were focused around astrobiology. But I was really glad that I maintained sort of that grounding in that other discipline. So I recommend thinking about which types of science you're really passionate about, and so many of them have a link to astrobiology. Like, that's what I love about astrobiology. It's so multidisciplinary, and that's what makes it so fascinating, and that's what helps us make progress, right? Like, I'm the only, I may be the only chemist that works around me at all in my group at NASA. And so I work with a bunch of people who all bring some other, sort of expertise in terms of their training, but then together we can make connections, and we can come together and kind of build something like that. So that's the advice I usually give.
Awesome. Yeah, and I noticed in your bio, so I'm a past AbGradCon organizer when we had it at CU Boulder in 2016. We just had our last episode of Ask an Astrobiologist was focused on AbGradCon and the importance of things like this, like meetings and conferences where undergraduates and graduate students and postdocs can come together and share their research. And you were a past organizer of AbGradCon, I saw. I wonder if you can speak to the importance of AbGradCon and other meetings and networking in your career.
Oh, absolutely. I would not have my job if it weren't for astrobiology meetings. Actually, when I think about it, one meeting, sort of AbSciCon meetings I would go to every time they happened. When I was a graduate student, I was very lucky. I had an advisor who really pushed me, pushed all of her students to present at meetings. And get out there. And by presenting my research sort of on Titan, aerosols and early Earth aerosols, I made connections with one scientist who was very interested in working at Penn State at the time, and then remembered that discussion years later when she was in a group at Goddard that was wanted to hire somebody new. And that's who passed my name, for example, to the person who ended up hiring me in my current job. And in addition to that, when I organized AbGradCon, I did so with two other people, one of whom was a postdoc at Goddard. So when the job opportunity came up, I was like, oh, hey, Avi, there was a job opening. Do you think I should try? And if I come out to give a seminar, can I visit you and see how you like it and what your life is like at Goddard? And that was my first friend. But I did.
Awesome.
And now it turns out both of the people I organized AbGradCon with, we all work at Goddard, all three of us.
Awesome. Yeah. So, I became the host of this show because of AbGradCon and meeting Sanjay Sam and the folks who run Blue Marble Space and SaganNet and becoming friends. And it led to me being here now, too. So that's wonderful. There's one more question that just came in that I really want to ask because it's a really cool question. Going back to Titan, can Titan, so you mentioned how Titan has this bedrock of water, ice, and we've discussed, this sand particles of organic material. So user @RogueZebraTMR on Twitter wants to know, can Titan have different types of rocks? Could it be like, we have igneous, metamorphic, sedimentary rocks. Are we also categorizing rocks, that this icy material on Titan in the same way?
So we will. I think, I really believe we will. At one of our earliest science team meetings, we talked about how we're going to be sort of writing the mineralogy of Titan with the kind of studies that we can do with Dragonfly. And I think knowing what we do know now, I have every expectation that we'll find evidence, right, of sedimentary formations, but it'll be made of things that are affected by liquid methane flowing over them instead of liquid water flowing over them, right? We expect to find maybe even conglomerates of like water ice chunks, but maybe they're an organic matrix or vice versa. And we know we have like these impact melts, and so I think absolutely we're going to be classifying all the materials that we find, and it's going to be a lot of parallels because that's how we study other planets, right? We take what we know from Earth and we apply it to those other systems.
Awesome. Do you have time for one more question, Dr. Trainer? Yeah, okay, awesome. So one more question, and to all of those asking questions, thank you very much. We're not going to get to all of them, obviously, but I do appreciate everybody asking your questions for Dr. Trainer. Our last question comes from Azul again. She wants to know, in terms of resistance design, how does the Dragonfly spacecraft differ from the Huygens spacecraft, allowing it to have that much longer of a lifespan?
Oh, it's power. It's 100% power. So the Huygens probe is powered with a battery. And so eventually the battery just runs out. Whereas, as we talked before, the idea is that Dragonfly was designed to be powered with a nuclear energy source that can last much longer for years and years.
Oh, that's wonderful. Well, Dr. Trainer, thank you so much for joining us for Astrobiologist. I'm way more hopeful now about Dragonfly. I'm so excited for this mission. There's so much more to learn. So hopefully folks can reach out to you if you're okay with that. You are at planet_trainer on Twitter, and I think folks can find you there and ask more questions. And thank you for joining us for Ask an Astrobiologist.
Thank you so much. This is so fun.
It was great having you. For everyone watching, if you're interested right now,
See if you can pull up that APOD. Turn this mic on. Oh, we are on. Well, that was interesting. This was made in fall of 2020, I believe. And when I looked up Dragonfly on one of the NASA sites, it's now scheduled for launch in sometime in 2027. So they still have a while to get everything done and learn more about what they need to do. But this is breaking news. It's been on, it was on the television news, it was on Science Friday today. This is Sagittarius A star. This is the center of our Milky Way. This is the black hole that's in the middle of our Milky Way, a little insert there. It's about 4 million solar masses, which is kind of small for a giant black hole, because some of them are tens of millions. But they took this with the, well, you can scroll down, Dan. They have a set of telescopes that are spread across the entire Earth. What's the name of it now? Yeah, there it is. I can barely read it. Event Horizon telescopes, and they're radio telescopes, and they combine the signals to make an image of the region around the black hole. And so the glowing ring, can't see the black hole itself, but we can see the materials that are swirling around, reaching millions of degrees and giving off radio energy so that they can detect where they are. But if you'll scroll down there, there's a little movie, Dan. You see where it says observed to orbit, first line, second little blue link. This is over a period of years. These are stars very close to the center of the galaxy. And you can see that these stars are swirling around a very concentrated object of intense gravity. I saw one of these a few years ago. It was longer than this, and you could see them come in and whip around and take back off and come back in again. These are stars that are just not right at the event horizon, but they're close enough that they can see the difference in their positions over just a few months to a few years compared to stars in our own solar system or galaxy. It takes tens to hundreds of years to see them move a fraction of an arc minute. So anyway, that's you can look at that. This is an astronomy picture of the day. It's real easy to find, just APOD. And if you want to look at it tonight, or you'd have to look at it, if you look at it yesterday, tomorrow you can click back to previous dates. So that is in the center of our galaxy toward Sagittarius, and that is our own supermassive black hole. So does anybody have comments? Turn up the lights down. I hope we all learned something tonight. I would invite you to come out on the 20th for our guest night, and on the 27th for our members night. I have a group of students from ORU. These are kids going into 8th or 9th grade on Monday, June the 6th. They've been doing this since, I've been working with them since '99. But they're going to get to come back, and so we'll need some volunteers that night to just set up some telescopes and show them around, and they're usually pretty well behaved. They're pretty smart kids. They have to apply for the NASA Science Academy. So somebody had a question?
Well, I was just wondering if you knew if we only have one black hole, or if it's possible some galaxies have more than one.
Brad, did you want to field that? He wanted to know if we have only one black hole, or do galaxies have more than one black hole, supermassive black holes? I think the answer to the second one is yes.
come in varieties on. We just have one.
Probably a good thing.
That may be-
Now, there are some of them that have masses of tens of millions of solar masses.
Oh, yeah, there is that one, I'm getting the answers. There is that famous one, I can't think of the name of it right now, where it's got the two galaxies, black holes converging.
Oh, yeah, I did see a clip on that on the internet. The two of them seem to be going to be merging. That will be quite interesting. All right, if you, some of our members go down the street, just get out here on the street, go to the corner just before you go, turn toward the bridge, and there's a place there called Louis, and you can get a good sandwich there and visit. So, some of them go to there, you're welcome to join up with them there. All right, well, we thank you all for coming, and look forward to getting acquainted with our new members. And don't forget the lunar eclipse, invite your neighbors out, take a look at it. There's the times. All right, thank you.